So what's the relationship between R and H? How do you get there? What do you set up? What can you set up to get there?
R over 20.
So say again?
R over 20.
So R to 20, little piece to big piece. So you got these similar triangles here, right? So this side of this triangle to the same side of the big triangle, that ratio has to be the same ratio as H to 60. You could have also done little r to little h is equal to big R to big H. It's the same thing mathematically, right? So if you take that down there and that up there, it's the same thing I just said. So there's a lot of different ways to set up this proportion. It doesn't matter because I'm going to solve what I'm going to solve for. H. I'm going to solve for H because then I can replace H with what I end up with. I want to get rid of H. So I want to solve this one for H. So what do you get? H equals 3R. So the height is always 3 times the radius. And you can see that. It's neato. But that's why it works, because in a cone I've got these triangles, and that's how similar triangles work. They always maintain that multiple. That multiplier always is maintained. How are we doing so far? So what does my volume formula become then?
It's 3R.
3R. So that's nice. So I get volume is now pi r cubed. I like it. For this cone, that's the volume of the water at any radius. Okay, I like it. Did anybody get there? You guys got that function? No? No. Yes? Do you see how that works? Do you see how now almost any conical problem might have something like that in it? Maybe? Okay. So what do I do now? So that's part A. Volume as a function of radius. Yeah, it's crazy. So part B talks about at what rate is the radius shrinking when the radius is 16 feet. So I'm draining this tank, right? So what do I know? What does the problem tell me? It tells me that what's the 48?
That's dV/dt.
And what's not quite right about this?
It's shading out.
So it should be
It's negative.
negative. I like it. All right, negative 48, whatever's pi. It's negative 48 pi. I think I was trying to be nice with that choice of units. Man, that's precise control of volume. Negative 48 pi, exactly. I like it. So that's what is given to us. I also want to know, so now I want to know what's it in symbols that I need to know. What do they ask me for in symbols? dr/dt. Cool. At a time when the radius is 16, I like it. Kick ass. Now, you just take derivative, like you said. All right, so what's dv/dt equal to? Who to what?
3 pi r squared.
Yeah, 3 pi r squared, and then the chain rule piece, dr/dt. That's the easiest thing to forget is this poor little dude. But you should quickly, well, that's what they're asking me. If I don't have that show up in my equation, how the hell could I ever answer the question? Shit, it's got to be somewhere. All right. What are we doing so far? I mean, this is exactly the same problem we've done several times already, just a different physical situation, but it's the same idea. Draw the picture, write the equation that models the thing you're talking about. Too many freaking variables. Okay, so figure out how to get rid of one of them. And then, now I've got an equation that relates the variables of the problem. Let me take derivative so I get an equation that relates the rates of change of those things. So now I just plug and chug. Right? What's R? 16. And what's dv/dt? Negative 48 pi. Now you see why I put the pi in there. Yeah, 3 times 16 is 48, and 148 pi cancels, right? And then you have a 16 left, so it should be 1/16, right?
Yeah.
1/16 what?
Mine. Cubic feet.
Negative, yeah, thank you. Where'd it go? Yeah, cubic feet per second, yeah.
There should be only 1 foot per second.
Oh,
Why is that?
It's radius.
It's radius squared, yeah. So 3 times 16 is 48, so that would cancel. The pi's cancel, but I got 1/16 left, right? Because it's 16 squared.
So what are the
The
units?
units.
That should be 1 foot
Oh yeah, I'm sorry.
per second.
Thank you. It's not volume, I like it. Thank you. So it's just changing radius, and the radius, thankfully, is not cubic feet. It'd be a freaky world. Let's see. All right. So that's part B. So that was relatively easy because it just told you what R was. You didn't have to solve for it. Now, who's got a realization for part C? There's something up here that would make this really fast. Do I have to go back and solve for R and then replace it? Or do I have an equation that relates what I know with what they're asking me? I do.
Yeah.
Right there. So what's dH dt? So this is part C. What's dH dt? Equals to 3 times dr dt. I know this, and they're asking me for this. Do you guys see what happened here? Right? I mean, any equation I have that relates variables that I know something about and want to know something about, I can take derivatives and use it. So if I can write a volume formula for a shape, I can take derivatives and use it to figure out how quickly something's changing. Right, that's the main idea. But we have this stupid little equation that we didn't even realize was important beyond what we used it for already. Holy shit, it tells me how H and R are related. Don't I know dr dt? We just did it. So what's dH dt? 3 times that. So negative 3/16. Get out of there. Feet per second. You could go back, solve for R, plug H over 3 in here, do the whole damn thing again, and finally get there. It'll work. It has to work. Oh my God, why would I? So there's a few different things going on here. Why did I solve for the radius? Because you were told to, number one. But even if I didn't put part A there, just started with part B, you would solve for H in terms of R because it's asking you dr dt. It's asking you about that. So I want a function that has R in it. Maybe. And I don't know if anybody, I have a feeling the answer to this is no, because you all still look like you're desperately trying to hang on. But if I took this guy's derivative just the way it is, what would I have to use? If I just took this guy's derivative right now, bam, just right now, immediately. Product rule, right? Isn't it R squared times H?
Yeah.
All this message is constant. So you totally could do that. So it'd be 2RH dr dt plus R squared dH dt. Oh my God. If you wanted to. And then you could do this work first and replace dH dt with 3 dr dt, and you can solve for dr. Oh my God. Why would you want to? I don't know. But in case you were curious, of course you can. Right? We know how to deal with more than one variable. We just... Product rule in this case are 2 functions of t. Right next to each other. Product rule. Okay. So you draw a picture that represents what's going on. You write the formula that represents that, which you just drew, right? And has all the parts to it that you're interested in. If you have too many variables, I would highly recommend not doing this. Just go ahead and figure out how to replace a variable with another variable. And then take derivatives. And then you start plugging and chugging. Right? That's how this works. Very often the hardest part is setting up the equation, but this time it wasn't that hard. It's just, I gave you this equation. So any questions on that? So there's a few cone type of problems in the homework, right? So you can expect something like this to happen. Right, there's that. I think I assigned that classic problem about sand falling in the shape of a cone, because it often does actually, which is kind of weird. Right? And I also like a problem about stalactites and stalagmites forming, right? in Ks. Let me see if I can throw something else on top of here. Sure. So what did we figure out? We figured out that at a time when the radius is 16, it's changing by 1/16, it's decreasing by that much per second, right? The radius is. All right. And that's happening because the volume is changing at a constant rate of 48 pi cubic feet per second. Okay. All right. So watch this. Watch this. Stay with me now. So everybody got this part here? I need some room. I'll take this. Yes. Okay. Stay with me now. Now watch. What is the volume at when R is 16? What is the volume? What is that volume? What would you do? What's the volume formula that we use that has only R in it? Yeah. So it'll be pi. Leave the pi in there. So it's pi times 16 cubed, right? Somebody help me out. What the hell is that?
4,096.
Do it again. 4,096 pi cubic feet. Let me stop there for a second. All right, now what? Let me see if I can do this one. I'm going to bring something tomorrow that's got I got to decide on what I'm bringing. I got a stalactite. Maybe I'll bring the stalagmite one. Because you guys look really super excited when I said that. A lot of spelunking people in here. If I wait 1 second, how big will the radius be now? The radius is currently 16 feet. You could do it. If I wait 1 second, how do I figure out how big the radius is now? That seems to mean I need to know how quickly the radius is changing. If only I knew that. Yeah, good. The radius is changing by 1/16 foot, it's decreasing by 1/16 of a foot per second. So if I wait 1 second.
15 and 96. Or wait, 15 and 15.
Yes, so after 1 second, the radius will be 15 and 15/16. Are you guys with me so far? So what am I doing right now? I'm going beyond the problem. I'm just kind of plugging some numbers in to see if it makes sense. The volume, if I calculate the volume right now, can somebody estimate what it should be? How much is the volume supposed to be changing per second?
Yeah, -45. -48.
Negative 48 pi. So it should be about 4,048 pi. Do it. Exactly. So what is 15? Basically, what is 15 and 15/16 cubed? Help me out. Put 15 and 15/16 in parentheses if you do it that way. All right. We'll do 15 plus 15 divided by 16 and then cube that whole thing. All right. Some way to do that.
2,700.
Uh-oh. Something went wrong.
Did you cube it? No, the symbols are wrong calculation.
It's about 4,048.
Was it?
4,048.19.
Yeah, don't put pi in there.
Yeah.
Right, because it's in terms of pi. I left it in terms of pi just to make it easier to work with. You guys with me?
But it's as you said, right? It's changing by minus.
Yes, exactly. It better be, right? I really want. So there's the concrete side of this. If I do, so I kind of did it backwards from the way the problem was set up. But if I let the radius change by this much, that must mean a second went by. Therefore, the volume has to change by about this much. Why isn't it exactly this much? Why is it not exactly that much? Why does that not mean I made a mistake or anything? It means everything's perfectly fine. I wouldn't expect it to be exactly this much. Why?
What's the rate of change at the next time?
The rate of change itself is changing possible, or yeah, exactly. I like it because this is how fast the radius is changing when the radius is 16. The minute, the second, the nanosecond, the picosecond that is not 16 anymore, the rate of change is now different. So this is like when we first did derivatives, before we even knew they were derivatives. We took a point and got closer and closer and closer, right? We never got close enough to be exact. Because how close do you have to be exact? right on top of the damn thing. You can't do that. Too bad. You guys, so it was never perfect. We just saw the pattern. We said it looks like it's going to 6. So here, it should look like it's trying to be this. And I would totally say that went down by about 48. Right? I wouldn't look at this and go, your entire theory is wrong. 0.19, give me a break. Do you guys see that? A little bit? You guys actually woke up a little bit there. Because we were like, oh, freaking concrete numbers. Yes. I'm not joking you either. I understand how it is. You're like, please give me something concrete. So if I let a second go by and I change the radius by the amount that it should be changed, the volume does change by the amount it should be changed. That's a nice concrete thing you can do. That's really what we're doing. We're trying to figure out if the volume is changing by this much, I should be able to figure out how much the radius is changing because they're related to each other. Again, the frickin' title of the section. Okay, maybe. What about the second problem? Has anybody got to that one yet? The balloon. I like that problem because it's got, I would, but it's got, it's a 2-layer kind of problem. There's 2 functions there, right? It's got to be a 2-layer kind of problem.
So you do the derivative of the volume formula and get dV/dt?
I love it, and it makes sense because.
Surface area?
See again? Sorry?
It would be the same thing as the surface area, right? The equation, the derivative?
Well, the derivative of the volume with respect to radius is equal to the surface area. But I'm going to take the derivative of the volume with respect to time. So it's a little different, right? So I've got 2 things here. What is it that they tell me directly in symbols?
dV/dt.
Yeah, they tell me dV/dt. Minute, right? All right, change it up. Oh. So if you're stuck, this is why I desperately want to give you, even if you have no idea what the hell to do, you should be able to look at the units and figure out how to write this. That's why this is better than V prime in general, to be honest, because it actually has a lot more information in it. You can see the units that should be there. And what is it they ask me about?
dr. Yeah.
Do who do it?
Radius.
Area.
No, what is it that they ask me about?
Oh, it's
How fast is the surface area? So what's that in units?
Yes.
I mean, in symbols. ds dt equals, I don't know. So that's what I'm being asked about, right? They tell me this, and they ask me that.
Isn't it a negative 4 since gas is escaping?
I like it. So -4, kick ass. Okay, so the volume formula is given to you. So this is not one where I've got to get rid of a variable because it's only got one variable to start with, kick ass. This is a different kind of double layer problem, right? What is, obviously I wanted to figure out what dV/dt is. So what's dV/dt?
3r squared.
So somebody said the 3's will cancel, right? So you have 4 pi r squared dr/dt. And they're asking me for this. So at the same time, let me go ahead and plop down the surface area formula, which is inside the derivative volume, but right? And there might be something I can do with that, but we'll see. And what's ds dt equal to?
8 pi r
8 pi. Yeah.
Do it again.
8 pi.
8 pi r
dr.
dr dt. Like it. So there's 2 ways to do this problem. One is very direct. It's exactly what I'm doing up here. And the reason, if you had no idea what to do, but you could write these down, then you know, well, you got to freaking take the derivative of the volume because you got a dV/dt, and you got to freaking take the derivative of the surface area. You got to go freaking ds dt, right? Even if you had no idea what the hell to do, there, you can start there. What's the connection between these 2? dr dt is the connection between them, right? So to figure this out, I need to know this. And I can figure this out because I know this. Do you see that? I like it. All right, finished. Especially all the people that just went, yeah, I see that. Now, there is a different way to do this problem, but we'll see. Somebody else comes up with a different way.
-1/3.
I don't know. We'll find out. All right, let me catch up to you guys. So here I can plug here the -4. And I tell you at a time when the radius is what?
16, or 24, sorry.
R is 24. So you can solve this for dr dt. 4's cancel, so it'll be -1 over 24 squared pi, whatever the hell that is.
256, I think.
Sure. And see, I would leave it like this, because then you never know what's going to happen over there. Yeah, so don't even multiply pi, especially when you have multiple equations. You're hoping to God pi is going to cancel. If it doesn't, then you worry about it, all right? But look what's going to happen immediately. So ds dt equals 8 pi r.
24.
R is 24 at this moment. Dr dt is -1 over 24 squared pi. So see, what happens?
24 and
Pi cancels.
And 1 of 24.
One of the 24s cancel. And 8 goes into 24 3 times. So I do get -1/3. -1/3 what?
Centimeters.
It's a square. It's a new square.
centimeters.
Good. It's area.
1 minute.
Square centimeters per minute. That's how much the surface area is changing as it lets out gas, right? Poor little balloon. Real quick. This is kind of neat. I wish I didn't have to do anything with dr/dt. That took extra time. I was like, God, what? This is kind of cool. What is ds dt divided by dv dt?
DS over DS over TV.
No. Don't do anything with the dt's or anything, right? Won't it be 8 pi r dr dt divided by this, right?
Yeah.
Okay. So 8 pi r dr dt divided by 4 pi r squared dr dt. dr dt cancels. 4 is 8 twice. The pi's cancel. One of the r's cancel. So I get ds dt. Multiply this up equals 2 over r dv dt. And what's dv dt?
-4.
224. What was it? I'm sorry.
Negative 4. Top. Negative 4. Negative 4 centimeters.
Oh yeah, that's right. -4. 4 goes into 24 6 times. 2 goes into 6 3 times. Negative 1/3 done. Thank you very much. Blah, blah, blah. Right? Again, it's not, so what, I know what to do. Big deal. I've seen a lot of this shit. So I know the flexibility that I'm allowed. You guys would, I would be really surprised if somebody would have thought of that. It would have been really kick-ass cool, but it would not have been easy to think of that. Because you don't even think you're allowed to do that. Why are you allowed to do that? Because nothing's zero. Right? I'm not letting anything be zero. If something was zero, then I couldn't take the ratio, right? But I know that things are not zero in this realm that I'm working with. Are you with me? So I'm totally allowed to do that. You did that kind of thing in trigonometry when you're like dividing to get rid of some trig stuff. I don't know if you guys remember, but that came up decently often in your trig, or should have. I want you to realize, if you don't see this, it doesn't matter a damn bit. You do this. This is fine. You do the first thing you think of and you follow through. You don't worry about, is there a better way? Let me try to come up with better. No, attack it the way you think about it. Right? But I just want to slowly show you the flexibility you have in math. This is what you don't get to see often enough, so you can't even come up with it yourself, because you didn't even know you could do this kind of shit. You totally can't. Look, it comes up with the right answer. Holy shit, yes.
Can we just find drdt in both and then equalize them?
Of course, yeah. You could solve for drdt and plug it in, which is essentially what I'm doing there. Just a little more directly, right? So if you solve for drdt and plug it in, you'll end up doing what I just did mathematically. I like it. Cool. But does it matter if you didn't think of that? No, there's that way. That wasn't that much longer, right? You just gotta, think of one way to do it. See how much time we got? A little bit of time. Number 3. Go ahead and take a couple minutes. Try to set that one up. Real quick, what's the angle of elevation? If I'm looking straight out, what's the angle of elevation? From the ground up. It's the angle that I have to actually crank my head through so I can see it, or at least move my eyes up if I don't want to move my head. Right? It's that angle that I have to look at. So it's going to be this base angle in the triangle. Okay. Which can be moved if you need to.
So 300 miles per hour?
Yep, miles per hour. So you got to be careful about the fact that you're letting 10 minutes go by. just so I didn't have to move my angle around, I decided, what's this going to be?
3 miles.
3.
3 miles, good. And what's this going to be?
3.
Yeah, because it's 10 minutes, which is how much of an hour? 1/6 of an hour, so after 1/6 of an hour, it's going to go 50 miles. I like it. Let me stop there for a second.